Welcome to the Communication Software Lab of MATLAB. The aim of experiment is to demonstrate pulse amplitude modulating wave. We have a carrier pulse train as shown. Modulating signal is a sinusoidal signal. The pulse amplitude modulated wave is the carrier wave whose amplitude varies according to the instantaneous value of the modulating signal. So bipolar PAM is shown here because it has both the polarities. We can have unipolar as well if the negative portion of the pulse is shifted to the positive side by addition of amplitude to it. A fixed amplitude is added to it, it will shift to the positive side. So both bipolar and polar are shown in the single slide. Let's go to the coding part. So I have Octave Online. Let's take T. So let me just have T varying from 0 to say around 1, from 1 to 0 to 1 second. I can have zero to 1 second. I'm going to have my graph with interval of 0.001. AM is suppose 0.4, even AC is suppose 0.5, given, and FM is equal to say around say 8 Hertz, and my FC is 10 times, so FC is around 80 Hertz. So this has been given to me. Let my modulating signal is equal to AM into cos of 2 pi FM train of pulse is shown by C is equal to AC square to by FC T. This is a square wave which varies from plus AC to minus AC. So if I want all my pulses, the square wave, to be on the positive side, then I need to add AC to it. The pulse amplitude modulated wave, which is bipolar, is given by bipolar PAM, bipolar PAM is given as M dot product of M message and the carrier C. This is the bipolar PAM. If I want the unipolar PAM, I need to have um, a loop such that my unipolar remains in this matrix here, stored in this matrix, such that if I use my for loop, in which the I is from first sample to the lastmost sample of the um, bipolar PAM. So if bipolar PAM is 0, its bipolar PAM is equal to 0, then you don't need to add anything, just put it straight away. So if it is equal to 0, then the unipolar PAM will remain same. So it will have it will be equal to unipolar PAM. It will be same and joined with bipolar. Be same. Else, if it is not equal to 0, then else it will be unipolar will be equal to, you have to add there, we have to add a constant to it to raise it. So let's raise it about by 2, safer side. It's just double the amount of the carrier wave amplitude. So I've taken 2 here, and this loop, we end the loop. Now let's just subplot and plot all the graphs. So I'll have 4 graphs. So this is the first graph. Plot. First I'm going to plot the message signal. So T comma M, title, the modulating signal, next is the train of pulses. Second graph, the next is the bipolar 413. dipolar band, subplot, 414, fourth graph, plot, T comma, unipolar band, and title, unipolar, pulse amplitude wave. So here we have these four graphs in signal slide, and the top one is a modulating signal, next is the train of pulse, that is the carrier, and then we have the unipolar, and the last one is the bipolar. So we are done with the pulse amplitude modulated wave. You can try out with different amplitudes of the modulating signal, change the amplitude and keep it around 0.5, 0.6, 0.7, less than the carrier, and then change the frequency of the modulating signal, take it to 10, take it to 12, and FC should be 10 times to that of the modulating, keeping it into account. So we are done with this pulse amplitude modulated wave generation by MATLAB.